Hello, welcome to section 5.1. This is about a pretty new concept, so if you felt like you were getting behind with all of the quadratic functions in chapter 4, and you were worried that you wouldn't be able to catch up, this is a little bit of a chance to start over because it's a new concept and we're going to approach some kind of old things we've been doing before, but in a new way with this new kind of notation. So, anyways, let's look at this first example where we're going to explore what it means for an equation to describe a function or not. So here we have two equations, equation A and equation B. We want to see is it true or false for each value of x in each equation, is there only one value of y or not? So first, let's just pick some values of x. I don't know. Let's start with like -2, a nice negative number here. So the y coordinate there is going to be the x coordinate squared plus 3, and we're plugging in x equals -2 into that. So -2 squared becomes +4, and 4 plus 3 is 7. So that gets you that, and you can keep going with this. Maybe plug in -1, 0. We'll get -1 squared plus 3 becomes 4, because it's 1 plus 3 is 4. And if you do 0 squared, that's 0 plus 3 is 3. And then I'll pause it and speed this up a little bit. And so here's some more values in the table. I plugged in some values of x and got these values of y as a result from that. And you could use this, of course, to make a graph now or answer some other questions. But I want to answer this question right now. For each value of x, is there only one value of y or not? So, for example, if x is -2, is there one value of y that goes with it? Yes, there's only one number, -7. Even though there's another value of x that goes with that 7, that means that there are some values of y that correspond to two values of x. But that's not what the question's asking. The question is asking for each x, if you pick a particular number for x, do you only get one y from that? And the answer to that is yes. So this statement is true. Okay, now let's look at this one. I'll pick a value of x. Let's say maybe x equals -4. And if you plug that into the formula here, we're going to do the plus or minus square root of -4, which is imaginary. It is plus or minus 2i. So the square root of 4 is 2, and then the square root of the -1 becomes I. And that does represent two different numbers. So we could write one as 2i here, but then you could also plug in -4 and get -2i. So that's how that goes. But if we don't want to think about imaginary numbers anymore, let's try maybe some positive numbers like 1. If you do the plus or minus square root of 1, well, it's either plus or minus 1, so that would give you a positive 1 here, and also another value point in the table where x is 1, and the y could also be the negative square root of 1. Likewise, if you plug in something like +4, I'm just picking ones that you could take the square root of. That gives you the positive or negative square root of 4, which you can then write as plus or minus 2. So that gives you either 2 or -2. All right, so let's answer this other question. Is it true or false that for each value of x, there's only one value of y? And looking at this, I can say, no, that's not true. Each of these values of x that we have in the table here goes with two values of y. Now, that leads us to our definition of a function here. So some relationships between variables are functions and some are not. One that makes a relationship between two variables a function is whether or not this is true. if there is a unique, meaning only one, value of the output variable assigned to each value of the input variable. So in our case here, the output variable is it's usually y, but sometimes it could be all kinds of other things. And our input variable was x, because that's what we plugged into the formula and we got a result for y. And so that means that here, with this first one, you can say that y is a function of x. We usually say of x to mean that that is the input. And with this one, you can definitely say that y is not a function of x. So there's some other function notation that we should introduce here. We're going to use a different letter other than the two variables to stand for the name of a function. And the most common one is f. If the name of this function is f, we can write function notation like this. We can say that y is equal to f of x. And we read this, like I just said, as f of. And the of is important in function notation because whatever's after the of, whenever you're reading about this, because a lot of the questions use different kinds of language, or talking about it or hearing me talk about it, whatever comes after the word of describes what the input is here. So we can say that y is the output variable, x is the input variable, f is the name of the function here, and then you can use this to describe certain things. Like you can say, for example, what is f of, I don't know, 7. So if that means what is the result, because f of 7 stands for the result y when the input is 7, and this comes out to be 7 squared plus 3, also known as 49 plus 3 is 52. So you can say that if the input is 7, the output is 52. That's what this means. And you want to think of a function as like a machine. You've probably heard this analogy before if you've had intermediate algebra or trigonometry or anything before, where the machine like takes inputs like x and gets a resulting output called y in this case. And if you take particular numbers for x, you're always going to get some particular number out. Like if you input 7, the output is going to be 52. And if the input is, I don't know, -2, the resulting output is going to be, 7. So, but that doesn't work here because if you plug in the number like 4, for example, you get 2 or -2. So this is not a function, and that's the difference between what is a function and what is not a function.